10.1.1. We're going to do a little bit of statistics. I will freely admit right now that statistics are definitely a weakness of mine. So anyway, we'll sort of get through it. It's basic statistics, so for the most part it's fine, but there's a couple of questions that kind of go between integrated 1 and integrated 2 that I'm not sure exactly of the answer of. But anyway, I guess we'll get started and go from there. So association in two-way tables. In Chapter 4, you determined whether there was an association between numerical variables and how to describe that association. You studied the numerical variables of distance from a wall, form, length, points scored in basketball, and number of pizza toppings, among others. But data is often collected in categories instead. Categorical data includes your gender, what courses you're taking, what type of shoes you're wearing, and what brand of hamburger you prefer. Anything that cannot be graphed on a number line. Categorical data is often collected from surveys. Probability can be used to help detect whether there is an association between categorical, easy for me to say, variables. Probability has uses far beyond its origins in games of chance. Before determining probabilities, it is important to organize the information into non-overlapping mutually exclusive events. Or mutually exclusive events, I should say. In the past, you may have used Venn diagrams for this purpose. A Venn diagram showing the relationship of two events, A and B, is illustrated right. So a couple things. Again, you should have, regardless of whether you're getting this in class, in future years, or during the pandemic coronavirus outbreak, you should have the ability to get the Chapter 10 notes. I would strongly suggest having those available and sort of filling them in as you go, especially with the two-way table stuff, because we're going to talk about it a lot at the beginning of Chapter 10, and then we're going to transition on to other things, and it's going to be real easy to forget about what we talked about by the end of the chapter. So, again, just a suggestion for you as we go. So, we're going to start with 10.1. FAM is conducting, well, here, let me go ahead and I'm going to need some white space here, so let me go ahead and do that. Alright, so FAM is conducting a survey for the school newspaper. He surveyed 175 students at his school. He found that 28 had the new PiPhone, clever, 44 had the laptop computer, and 110 had neither. So draw a Venn diagram to represent this data and given information to figure out how many students are represented in each region. So let me see here. If I don't do a fill, all right, perfect. So this seems roughly like what I wanted. One circle is bigger than the other, but that's okay. So over here, we're gonna say how many people have the PiPhone. And this is going to be how many people have a laptop. We know that there's 175 students altogether. I will say, when we do this in class, often kids struggle with this for sure, and I can see why. So we'll talk about it, and hopefully it'll make a little bit more sense by the end. But again, you should be pausing this video and trying this for yourself before we go on to anything. So 175 students in the class, 28 have a PiPhone. 44 have a laptop, and 110 have neither. So we'll just put neither off to the side because they don't belong inside. That's unfortunate. You'd think I'd be better at this by now, but I'm not. Okay, so here's the problem. If I add up 110 plus 44 plus 28, I get 60, 72, 182. But that can't be possible because we only have 175 students. So there's something going on here. I think the suggestion would be that some of these people have to have both. So the question is, how many? Well, if we're off by 7, that doesn't seem like a bad place to start, right? Let's say 7 people have both. But if 7 people have both, this is saying 28 have a PiPhone only and 7 have both, so that would be 35 with the PiPhone, but we really only have 28 with the PiPhone, so I'm gonna have to change this to 1. So now if I read this, it says 21 with the PiPhone, 7 with both, that's 28 with the PiPhone. You can see I still have the issue with the laptop because I have 7 plus 44 is 51, so I'm gonna need to change this number as well to 37. Now, if I add up 21 plus 7 plus 37 plus 110, you can see I add up to 175 students. So this is what our Venn diagram wants to look like. Again, that overlap is sort of what's important there. So how did you determine the number of students that have both the PiPhones and the laptops? Well, like I said, it just kind of ended up having 7 extra students, so it made sense that 7 would have both to sort of get us to the number that we wanted. Now, how many students have PiPhones or laptops? Now, this begins to be one of the things, and versus or questions. You know, this is going to come up a lot in Integrated 2 and a little bit in Integrated 1, but you're still going to be responsible for it in Integrated 1. But it's a linguistic thing, right? If I'm in room 31 and in room 32 at the same time, that's really difficult to do. I can't do that, but I can be in room 31 or 32. So room 31 is more, I'm sorry, and is more exclusive. You have to be something and something else at the same time. Or is more, well, I should say less exclusive, right? You can be this or you can be this. So or is going to have more people in it than and is typically. It might be the same, but it won't have less. So how did you determine, okay, so how many students have the PiPhone or laptops? Well, these people have PiPhones or PiPhones and laptops or laptops. So I should be able to add all these together here and get 28, 35, so 65 students out of the 175, which makes sense because think about it. It's known as the complement. You'll learn this in Integrated 2. Not that you look good today, but I'm sure you do. But the complement means if 175 students exist and 110 of them don't have either, well, I can subtract that and determine that 65 must have one or the other. So again, you can kind of either add these together to get to 65, or you can use the complement and work backwards and get to 65. Again, that's going to show up in Integrated 2. Recall that 28 students had the new PiPhone. There's our 28. 44 students had the laptop. There's our 44. Why can't you just add 28 and 44? And again, we said because that just gives us too many people. So I hope that makes sense. Again, I know it's a little bit tricky for some people. Again, I hope that you're kind of following along as you do this and trying this for yourself and not just watching me do all the work for you, because I don't think that that's going to be super helpful for you. I get the feeling this is going to be a long video, by the way. All right, so let's go ahead and go to 10.2. Raul said he could not figure out how to put the data in the Venn diagram. And 10.1 is basically just to show you that Venn diagrams are possible, but we're going to kind of pivot from Venn diagrams. We're going to use these two-way tables instead. It has all the same information, except for the Venn diagram is except for the two-way table is also going to have column totals here. So here's the information that we were given from the other problem, and they're asking us to fill out the rest of the two-way table. Again, 175 students altogether, 110 have neither, 44 have a laptop, 28 have a PiPhone. How do we fill in the middle? Well, I could put 40 and 4 here, that's 44, or I hope you see I could put 41 and 3, or I could put 42 and 2. Literally, there's like an infinity of answers that I could put here. Although, since we're counting people, I guess negative doesn't make sense and partial doesn't make sense. But normally, you know, there's nothing stopping me from saying negative 1 and 45 to get to 44 either. Like I said, we wouldn't have negative 1 per people in this problem. That doesn't make sense, but in a lot of problems it does. So we can't start where there's two unknowns. So we can't start here, we can't start here, but we can start here because we know that 28 plus whatever this is going to equal 175. So if I grab a calculator or just do it in my head or whatever, I get 147. 28 plus 147 is 175. And now, all of a sudden, hey, look, I only have one unknown here. If I want, I could put 37 here. And now I only have one unknown here, so I can go here and put a 7. And now I only have one unknown, so I could put a 21. And then again, I can either add this or add this, and I get 131. One suggestion I would make is when you're done, I would add up all the columns, and I would add up all the rows. Don't just add up the columns or the rows, because if you make a mistake, you're not going to catch it. But if you do the columns and the rows, you'll definitely catch your mistake. So we have the 2A table completed. This type of table is called the 2A table. It's often used to organize information and calculate the probabilities. Why do you think it's called the 2A table? I don't know. I think it is because it goes in two directions. Honestly, though, I'm not trying to be smart. I have no idea if that's the right answer. It seems like it definitely would be, but I don't know. How is the 2A table similar to and different from a Venn diagram? What are the advantages and disadvantages? Well, it's similar, then it has a lot of the same information, but again, the difference is we have column totals where we didn't in the Venn diagram. So we were sort of left having to add the 7 plus 21 to get the 28 and add the 7 plus 37 to get the 44. Not a huge deal, but it's kind of convenient to have it just sort of looking at us. If we assume that FAM's survey is from a random sample of students in a school, what's the probability that a student at his high school has a iPhone or a laptop? And again, this is what's so important here. We're saying, all right, these people have a laptop, and these people have a iPhone, right? So if it's an or question, which it is, I don't care if it's these or these. Like, these people have both, that's great. These people have a laptop, no iPhone, but they count. These people have a laptop but no iPhone. I'm sorry, a iPhone but no laptop, so they count. So I should be able to add all these together and get my 65 out of 175, right? If it says, what's the probability that a student has a iPhone and a laptop? Well, again, this slash counts for laptops. This slash counts for iPhones. You'd have to have both slashes. You'd have to have the laptop slash and the iPhone slash. So it'd be 7 out of 165, 7 out of 175. Versus, again, the or question, you'd have to have the laptop slash or the iPhone slash. Either way. I kind of like to mark up my 2A tables as I'm doing them. You don't necessarily have to, but I find it helpful sometimes. So let's, you might notice some skipping in the video here. Essentially, when I did the first take, I had these backwards, the numbers. I was doing it off of memory, and I had the columns in the wrong row, the rows in the wrong order. So I want to come back and fix it. Anyway, we're going to move on to 10.3 now, association. And I just want to point out, again, I think it's a good idea to be filling out those forms. Definitely take some notes on association. We're going to do a little bit of it at the beginning of the chapter and then sort of get away from it as the chapter moves on. So you do not want to forget about this. Also, association is going to be a little bit different in integrated 2 than it is in 1. We're just going to be using like these columns. In integrated 2, you introduce the totals, which is fine. This is just sort of an introduction to it. So don't worry about that when you get to integrated 2. Okay, so if we look here, it says, is there an association between owning a laptop and owning a iPhone? So what does that even mean? Well, association lets us sort of see how groups sort of go together. For example, let's say I was looking for someone to dunk a basketball. I can ask everyone in the world, and not many people probably could. Or, if the Golden State Warriors were over there, I could go say, hey, NBA team, can you dunk a basketball? And I bet you there's a lot of tall gentlemen over there that can dunk a basketball. So if I ask everybody, the rate's probably really low. But if I ask an NBA basketball team, the rate's probably really high. So that's an association. The fact that, being tall and being on an NBA basketball team probably makes you more likely to be able to dunk. And it can be for like medical reasons. Some people might be more likely to get some sort of an illness. It might be for marketing. Like in this example is a good way of marketing, right? Why are we trying to figure out the association between laptops and iPhones? Well, maybe if I know people that own laptops are more likely to buy iPhones, then I can figure out who's bought a laptop and tell them, hey, you should buy this iPhone too, because they're more likely to do it. That's the kind of information you might want to know association for. So just to kind of discuss it real quickly, now we'll jump into the association. So in other words, if you own a laptop, are you more likely to own a iPhone? Investigate this question by calculating the probability that a laptop owner owns a iPhone. So we'll compare laptop owners and if they own a iPhone. Then we'll compare it to non-laptop owners and see if they have a iPhone. So, hey, all laptop owners, do you have a Pi phone? And what they're going to say again, I only care about laptop owners. I don't care about the non-laptop owners. I don't care about the totals. These are the only people I'm interested in. And 7 out of 44 have a laptop. I'm sorry, a Pi phone. So I would say that's 15.9%. Then if I compare that to non-laptop owners, and again, I'm asking them the same question. Do you have a Pi phone? 21 out of 131 would say yes to that. And it ends up at being about 16%. So you could see very similar numbers. I would say no association or an extremely weak association. There's no reason for me, like in that basketball example, there is a reason for me to go ask the Golden State Warriors to dunk this basketball. But in this problem, there's no more reason. If I need a Pi phone, it wouldn't matter if the person had a laptop or not. I'm just as likely to be able to borrow their Pi phone either way. All right, now the video should skip again, and we should go back to problem 10.4. So 10-4, there are 145 students enrolled in the senior class fitness class at Cooper High School. 116 boys, 29 girls, 24 of the boys and 7 of the girls earned A's the first semester. Create a two-way table like the one. Okay, so some hints on a two-way table. First of all, the total is going to go in the bottom right corner. The second thing is, as we're filling this out, if they tell us something like this is obviously boys and girls and A, not A, if they mention something that only mentions boy or girl or A or not A, it has to be a total. It can only go in the middle if they mention both. If they tell me it's a boy with an A or a boy with not an A or a girl with an A or a girl not an A, it can go in the middle. If they only mention one or the other, it has to be a total. And again, that's just a trick to fill these things out because sometimes people struggle. So 116 boys. It doesn't mention if they have an A or not an A. That must be a total. 29 girls. Again, it doesn't mention A, not an A. That must be a total. 24 of the boys and 7 of the girls earned A's. Well, now they're telling me both. They're a boy and they have an A. Or they're a girl and they have an A. And again, I can't solve where there's two unknowns. There's two unknowns. So here, 24 plus 7 is 31. I know that's got to be true. Here, this must be 114. 31 plus 114 is 145. Here, 7 plus 22 is 29. And then I can either do it this way or I can do it this way. Either way, I'm going to get 92. 24 plus 92 is 116 and 92 plus 22 is 114. Again, I would strongly encourage you, add up your columns, make sure that they add up your rows, make sure they add up. That way you don't get screwed up doing those things backwards. So there's our two-way table. Is there an association between gender and grade received? And again, in other words, is it more likely for a boy to receive an A than a girl? Well, I'm going to ask the boys, did you get an A? So this is the boys' response. 24 out of 116 said that they did. I'll grab a calculator. 24 divided by 116. I get a 20.7%. And now I will ask the girls, did you get an A? And it's 7 out of 29. So 7 divided by 29 is going to equal 24%. So is there an association? Yeah, I'd say a weak one. For whatever reason, the girls seem to have more A's than the boys as a percentage. I mean, that could be for a lot of different reasons. So it's not such a crazy association that I think necessarily sexism is going on right now. But potentially there's something going on that the girls are more likely to have an A than not. The boys are. So comparing percentages is easier in a conditional relative frequency table. That displays percentages instead of counts. Enter the percentages you calculated in part B into a conditional relatively frequency table like the one above. Note that the often totals are not included in the conditional relative frequency table. So let's look at a conditional relative frequency table. So we have boys, girls, A, not A. Those are our categories. By the way, when you make a table as well, it should be like categories, right? Like boy, girl, A, not A, I don't know, circle, square, whatever. It should be something like a yes, no, where we can easily sort of categorize things. You wouldn't want to say like boy A, girl not A. That would get confusing. So the things that are like next to each other, the things that are like next to each other, don't sort of cross them up, otherwise it gets difficult. Anyways, we're going to divide everything by the total. So we know there's 24 out of 145, so we're going to divide that, and we're going to get 16.5% or 16.6%. Oh, actually, I take that back. I'm sorry. I believe that we should be dividing everything by the column total. So I'm going to get 24 divided by 116, and we're going to get 20.7%. And then I'm going to divide 92 by 116, and I'm going to get 79.3%. Then I'll divide 7 by 29, and I will get 24%. And I will divide 22 by 29, and I will get like 76%. Rounded a little bit there. I was kind of running out of room. So this again is known as a conditional relative frequency table, and it makes those comparisons, I guess, easier. By the way, this is the last problem in 10.1.1 Part 1. This day is broken up into 2 days. So a researcher suspected that some blood types are more susceptible to DAPT genetic defect than other blood types. The researcher collected the following data to investigate, make a conditional relative frequency table to determine whether there's an association between blood type and the presence of DAPT defect. All the two-way tables in this lesson are displayed for convenience, with the variable across the top as the independent variable. So this is going to be the independent, this is going to be the dependent. That means you calculate percents for columns. So we should add up a column, and it should add up to 100%. Just like up here, how I was dividing by the 145, I was doing it wrong. I want to divide everything by the column total, and that will give me 100% for each column. So you got to be careful. Divide by the columns total and not by the overall total like I had started to. So anyways, I do need to get these totals here. So 0.3 plus 0.28 plus 0.07 plus 0.03, so 5865, 0.68 is the total. And here 137, so what, 8, 9, 10, 11, carry the 1, 4, 7, 10, 11, 2, 3. So it looks like out of 311. 69 to 99. Yeah. Okay. So now when I make this table over here, I'm just going to go O, A, B, A, B. And it's going to be DAPT and no DAPT. So what we want to know, and it's a good question, hey, are people that have blood type O more likely to get DAPT than people who aren't? Maybe A has the most. We don't know. So what we're going to do is, again, we're going to divide 0.3 by 0.68, and we're going to get the percentage. So it's 44% here. We're going to divide 0.28 by 0.68. So you're going to get 0.4 or 41%. Hopefully we know we're moving the decimal by 2, right? So 0.07 divided by 0.68 is going to be 10%. And 0.03 divided by 0.68 is going to equal 4%. So looking at this, it's easy to draw the conclusion, oh yeah, look at that. O and A are way more likely to get it than B and AB. But that wouldn't be fair to compare. There might just be a lot more people that have blood type O than AB, and that might account for the percent. So we actually want to compare them to each other. So now we're going to go over here and divide 137 by 311. And we're going to get 44%. So you can see, oh, geez, look, I guess a lot of people have blood type O, and they're not more likely to get DAPT or not based on that. Let's see if that's true for all the other blood types. So on this one, 131 divided by 311 is 42%. So again, off by a little bit, but not by enough that we are concerned that something suspicious is going on. And then here, and again, I'm just dividing 31 by 311 and 12 by 311. And you could see something suspicious happens here. All the percents are the same, but one, well, obviously there's some rounding going on, right? So I think this one adds up to 99%. This one rounds up to 100 because of rounding. But ultimately, we're comparing the column totals to each other, and we have that association. So again, make sure when you set up your two column tables, you do it correctly. If it's a total versus if it's not a total, that kind of a thing. Make sure you understand and versus or, and make sure you understand association, that essentially we're comparing one to each other. Like I said, an integrated 2 will involve the column totals in that, but for now we will not. I hope that's making a little bit of sense. Again, I feel like I really did poorly on this one. It's my first video of the day. So if you have questions, feel free to reach out. Thanks. Bye.